Welcome friends, this is Dr. Sachidanand Singh from Sankalchand Patel University. I am professor in biotechnology and I am helping in this module of protein modeling and analysis. The previous title which we studied was protein structure prediction method. So, in that we said that we will understand a software or a tool to understand this protein modeling. So, let us learn today modeling software, one of the modeling software for protein modeling through Modeler. So, what is Modeler? Modeler is given by Sali. Modeler is currently maintained by Andre Sali at University of California, San Francisco. It runs on the operating system such as Unix, Linux and Windows. It is freeware for academic use. It also has graphical user interface which is known as GUI, and commercial version are distributed by Aceleries. The ModWeb comparative protein structure modeling web server is based on Modeler and other tools for automatic protein structure modeling with an option to deposit the resulting models into Modbase. Due to Modeler's popularity, several third-party GUIs for Modeler are available. Easy Modeler is freeware and is one of the earliest third-party GUI for Modeler. Recent version of Easy Modeler is 4.0, which supports Linux and Windows operating system. UCSF Chimera has a simple interface to Modeler. PyMod is a free and open source plugin for PyMol and has a comprehensive interface for Modeler. It supports Linux, Windows and Mac OS as well. MaxMod is a standalone GUI for Modeler on Windows. So, this Modeler, which is a very popular protein modeling tool given by Andre Sali, here in this presentation their references are been reported. It is basically used for homology modeling and there are different flavors of modeler. One of them is loop modeling also. This loop modeling also supports wire dynamics. Thus, the protein modeling which is done through Modeler has to pass through few evaluation criteria that we also saw in the previous lecture, in which we said homology modeling can be done only for those unknown sequences which has more than 30% identity. Now, what is identity and similarity? Identity is like in a sequence we have leucine to leucine alignment, alanine to alanine, that is identity. And what is similarity? Similarity is positively charged amino acid, negatively charged group of amino acids, neutral amino acids. So, here for passing Modeler to utilize, it has to go as greater than 30% identity. Also, when through Modeler a protein structure is been identified as 3D dimensional, it goes through stereochemistry identification or cross check using ProCheck analysis. Finally, this also goes through ProSA for solvent accessibility test and to understand distance based pair potential methodologies. So, in this slide it is again the revision or repetition of the previous presentation or learning which we have done on homology modeling. So, to start with and to have a brief review how a modeler performs its homology is to have an unknown sequence. For that unknown sequence, a target has been identified using different database search methods using understanding UniProt or BLASTP. Finally, the target selection is been done and the sequence and the target is been aligned. After alignment, they have to go through building a protein. The protein which has been modeled or built can be done 2 times, 5 times or 20 times, depends upon the source and the efficiency of the computer. So, the protein which has been modeled has to now be evaluated. If during the evaluation the model protein does not passes, it has to go as the reverse process from again the target selection and the final alignment sequence which has to be matched has to be a better alignment strategy, and if the model is been evaluated, it will end the process and it can be reported. So, To give a brief about the functional parameters of modeler, modeler is a homology based protein structure prediction tool. The models are developed by satisfaction of spatial restraints technique, which obeys the NMR nuclear magnetic resonance methodology. It is built on Python libraries and other functions that helps to manage structural data and is also incorporated within. It is a very robust method to interpret model and to evaluate its energy, and it is also a key point of modeler. It's free for academic user under GPL scheme. This modeler is a Python based modeler technique. So, now dear students and friends, let us see how a modeler database or URL looks like. So, when we type in Google, we can see modeler, and this is the front page of modeler reported into their web page. So, we can see at the left hand side all these subcategories are been mentioned, and in the middle the explanation of modeler is been reported. We can see in the left hand subsection different level of help manual, online manual, frequently asked question are been reported, and left we can see the download portion also. When we click on the download and installation, we can see in the middle the different version of the modeler in the different subsections are been reported. 32-bit Windows operating system, 64-bit operating system, Conda and Mac OS it can be installed. So, we can go ahead step by step, and whichever platform we have, we can install modeler in that. So, scientifically, modeler is a program for comparative modeling written by Professor Sali's group. The program uses a scripting language, that is Python. The user provides an alignment of a sequence to be modeled with known related structures. Modeler automatically calculates a model with all non-hydrogen atoms. It is built on Python libraries and other functions that helps to incorporate within. It is a robust method to interpret model and evaluate the model, and as we all see, it's a free for academic under GPL scheme. So, we have to go to http://salilab.org modeler, and we have to start doing our process. So, students and friends who are very good in programming or are interested to do programming can type the coding in the version of Conda, or they can also install in Windows or Mac OS or Ubuntu. So, in Conda we can see we have to write $conda config and add Salilab. When it is installed, we have to put the key KEY instead of the portion 4x. Finally, it will be installed. In Linux and Windows version, the link provided, we have to click on there, and then we have to see the availability of modeler. There are different versions of modeler, and presently the 10th version is going on, but right now to work here we will work with mod 9.24 version. So, now to see homology modeling workflow under modeler, how we have to see and what are the filter criteria we identify for performing homology modeling. So, when we see a target and a alignment is done for the unknown sequence, the filter criteria to identify the target sequence with the aligned template or the target template is when it matches the sequence, the target sequence and the aligned sequence. When they match, has to have a filter, that is first one is E value, that is expected chance mutation value should be closer to 0. The coverage should be high. Coverage in the sense the sequence for which we have to identify a structure and to whom it is aligned should have a bigger coverage, then only the structure will be identified. Finally, we also saw that identity and similarity should be more than 30%, then only we will be able to make it as a filter for homology modeling. Second is the PDB protein which has been identified as a target for that template can be a pdb.pdb extension. That PDB file should be read and see that it has all the 3 x, y, z axes. In that PDB protein, we should also see its R value, R factor. We should also see its resolution. The lower the resolution, the better is the structure for taking as a backbone for developing the protein structure. So, this is also known as sequence based and structure based methodology for protein modeling. Finally, the segment, the target and template is been mapped and is been oriented to develop the structure. Finally, this structure can be done using Swiss model, which also obeys modular thing, and then it can be analyzed using SAVS or ProCheck. So, modular, as we saw previously, it satisfies spatial restraints. What we mean by satisfying spatial restraint is the structure which we have identified has to obey the force field. So, the force field which is being utilized in modular is CHARMM, CHARMM. So, using this CHARMM algorithm, the protein has been modeled and is been evaluated to perform a 3D structure. The template act as a guide where the new model is built upon satisfying the restraints imposed. So, when this model is start getting built, it goes in n number of times, and this CHARMM force field methodologies give the best possible stable structure by n number of repetition, which is also known as an optimization function which runs to minimize the restraints, finally giving the best model fit using modular. So, now let us see how the modeler starts with. So, when we start a modeler software or online programming tool, there should be an input, and through that input we will get an output. So, what will be our input? So, very genuine and a logical thing is we should have a template sequence for which we want to develop a structure. So, that should be the first thing, and second, for that template a mapping sequence, that is a target sequence, should be there to understand and to map for protein modeling. Hence, in input there should be one protein data bank atom file which is of known protein structure, and their alignment with the target sequence to be modeled. The output is a model for the target that includes all non-hydrogen atom. Hence, modeler can calculate sequence and structure alignment. However, it is better to prepare the alignment carefully by other means as well. So, to give as an input in modular, there are 3 input files. The first one is known as atom file, second one is alignment file, and third is script file. So, in atom file, the coordinates for the template structure is present. In alignment file, contains the alignment of the template structure and the target sequence. The target sequence which we are of interest about. Template structure is the one which already a PDB structure is present, and finally the script files are nothing but all the modeler has Python scripts in which we can do modification, and we can model our own protein by ourselves. So, we do not have to write the whole Python code. If we are very good in programming, we can start from the initial level of Python coding, but modeler gives, Salilab gives all the scripts which needs to be modified. The script file needs to be modified which are at .py extension, and then the whole process can be performed. So, what is an atom file? Atom file is nothing but it is a protein data bank atom file with coordinates for the template structure. Each atom file is named as code.atm or code.pdb, where code is a short protein code, preferably the PDB code. So, what is a PDB code? It is a 4-letter code with alphanumeric character. So, say for example 1fdx.atm, 1fdx.pdb. So, here we are presenting Peptococcus aerogens ferredoxin would be a file known as 1fdx.atm. It will be nothing but it will be a X-ray crystallography protein target structure which we are interested about. The code must be used as that proteins identified throughout the modeling. The atom set do not have to be superposed by the user before comparative modeling is done. So, for selecting the templates, significant different structures homologous in sequence to the target, one should be very careful about it. However, it is not always best to use all the related 3D structures as templates because the objective function may become too rugged. 6 template is a large number of template. When we are taking n number of templates, all of that level is known as multiple template modeling. When we are taking a single template to perform the protein modeling is known as single template modeling. If two relatively simple templates or similar templates have been solved at a high and low resolution, use only the high resolution template. So, those templates, those structures which has high resolution, we can identify the protein structure better. Other factors to be considered in the selection of template is ligand bound to the template and or target template structure from NMR or X-ray crystallography. Among them, ligand bound template or X-ray template can be a possible acceptable structure to be taken care. So, first one we saw was the atom file, the second one is the alignment file. What is alignment file? One of the format for the alignment file is related to the PIR database format. What is PIR database format? Protein Information Resource Database format. This is the preferred format for comparative modeling. So, we can see it starts with a angular right-handed bracket, then alphabet and then the PDB ID. Then the information is been given with some number and finally the amino acid sequence is given. If you see down, same angular bracket with alphanumeric character is reported. So, this is a kind of FASTA file format itself. So, as we saw the basics of the modeling by using Modeler 9.24, there are 3 files as an input which we require. So, now let us start doing the modeling using Modeler 9.24. So, here the example also given in Modeler is TV-LDH protein sequence which can be used to model a protein. So, here we will start with this TV-LDH ELI file is been reported and its PIR file is also there to understand and to initiate the modeling process. So, the second step in making a modeler compatible input format is to convert the FASTA file into a PIR file. So, for converting a FASTA file into PIR file is a very simple technique of taking up the same format and doing the alignment, that is from right handed angular bracket, then alphanumeric character and information about the sequence and then amino acid sequence with a star. We can see at the down yellow color one, the last line ends with a star. So, the first approach which will be executed is build profile.py script. So, utilizing the build profile py script, the yellow highlighted portion has to be modified as per our PDB protein. So, we can see we have a PDB protein known as TV-LDH. So, we have to change the portion at that yellow highlighted portion and need not to change the whole script, and as per the modification done and basis of the name of the sequence of our target and template, the build profile.py script can be run. So, to understand this build profile.prf file which will be the output of the Python script, we can see it will include all the filter criteria which we have already reported in the previous section to pass to become to run for modeler. That was E value, that is expected chance mutation has to be near to 0, identity, coverage, similarity. Taking all this, the template which will be taken will be as your PDB file. So, that also is been given as .pdb extension and it is been depicted as a red arrow. So, these all will give us the input and the understanding in build profile.prf file. So, after doing the build profile, now we need to compare the sequence and to assess which template is best by analyzing structure and sequence similarity. So, in this Python script, now the second thing after build profile, the second thing will be the script of compare. So, compare.py script will be utilized and we can see that yellow highlight portion has to be modified as per our file format which we have received after build profile has to be modified, and then this compare.py script will be run. So, here very clearly we can see 1, 2, 3, 4, 5, 6, 6 PDB proteins are being analyzed and been compared in sense of phylogenetic classification, and it has been understood that how they are as per their resolution and as per their comparison, how they are been more prominent towards our unknown sequence. So, we can see TVLDH has the minimum resolution, and accordingly we can select that TVLDH will be the base structure to go ahead for modeling. This whole methodology, which was done through Python script, that was build profile or compare, can also be done manually, as we have already seen in previous videos that this same set of approach can be done manually in the sense as separately by different database search. So, when we have a unknown sequence of point of our interest, using an experimental approach need to be first put into UniProt database to see whether for that sequence a structure is present or not, or any name is given or not. If nothing is there, then we need to put it into BLAST. In BLAST, what is BLAST? Basic local alignment search tool. In this BLAST, we have to do PDB BLAST, and in PDB BLAST, if we get more than 30% identity, similarity, query coverage and e value near to 0, we can select from there itself one sequence as a structure, PDB structure, and start developing our model using Python script. So, now what we have done previously is we have done a profile building. Finally, we have compared the sequence. Now, we need to align the sequence. The template and target sequence needs to be aligned, and this is based on dynamic programming approach through specific factors considered for structural information. So, the code for this is align2d.py, and you can see in the yellow highlighted portion and the above third and fourth line of the script. Accordingly, as per the name of the PDB file utilized, the chain and the PDB file name can be modified, and the same script can be utilized to run the code as align2d.py. So, align2d.py file gives us two file format, in which the PAP format, align2d.pap format, need to be opened into text file and can be analyzed. There we can see for our sequence, unknown sequence and TVLDH sequence is been mapped, and it is been shown by asterisk signs where and all identity and similarity is been reported. Now, finally, after doing the set of process, that was build profile, compare, align2d, the final stage of protein modeling is model single.py. So, to perform this model single.py is the last step to develop the protein model. So, in this Python script of model single.py, the yellow highlighted portions has to be modified as per the previous file formats which has been received as ALI format and TVLDH, and the sequence, the structure, the PDB structure, 4-letter code ID which has been taken into consideration. The down in the script you can see it gives us GA341 analysis and the model build score, that is our dope score, which it gives us the least energy calculation of the best model fit. So, here at the last but second line represent that we are developing 5 protein models, and among that 5 protein model we want to see which one will be the best protein. So, to run this code is model single.py code. So, we can see by running model-single.py Python script, we receive file, and in which the log file has to be opened, and we can understand that the log file gives us, as in the Python script also we have run 5 models, and we can see here we have received 5 model with their dope score and GA341 score. So, GA341 score represents a threshold of 1, which is all the models are perfect, and we can see the dope score. So, the least energy value will be the best dope score reported. So, among these 5 we have to select the best one on the basis of the dope score of least energy value. Finally, energy profile calculation can also be done, and a pictorial graphical representation can be represented by running this script, in which this gives us with the structure and the template, the best structure which we have identified, and the template which we have received. We can see how they are been superimposed, and we can calculate the RMSD, that is root mean square deviation of that already known PDB structure and the structure which we have retrieved, that how they are been aligned. We can see at the middle portion few deviation is there, otherwise almost the structure is aligned. But if you see at the far end, it has been little deviated. That portion needs to be more refined till now. If the structure is not perfectly fine, there are different methods to do that. Separate is multiple sequence alignment method, for which the Python script is known as salign.py. This is done when with the single template modeling the protein structure has not come out perfectly. So for this we can use this code to have multiple template. So the code is salign.py. In this methodology, when we start doing it up, it considers structure dependent upon the gap penalty and give us a best model, and give in the sense of model.py, and for this the code used is align 2D underscore mult. Why it is? Because previously we have done multiple alignment modeling. So here the code will change as align 2D underscore mult.py, and finally the script will run with multiple templates. So this was all about protein modeling using modeler, in which first was with single template modeling and second one was with multiple template modeling. In multiple template modeling, two more codes were added, that was multiple template and one was multiple sequence alignment one. To know more about this, we can also refer the documentation of SaliLab and to see the initial level of manual in Sali. The following links have been provided to see. The protein which is been modeled need to be again more refined, and that approach can be done through MD, that is molecular dynamics. It is preferable to do MD based energy minimization to minimize the structural clashes. To perform this minimization of structural clashes, there are different softwares and algorithm. One of them, prominent one, is GROMACS, NAMD, VMD, AMBER and other MD simulation software which perform this activity. Ideally 5 nanosecond is run for removing the clashes, and maybe 20 nanoseconds are done for removing the loop refinement. This is not a very standard but a proposed approach for removing the clashes. So till now we saw through modeler using Python script how modeler helps us in developing a single template modeling or a multiple template modeling. There are many graphical user interface modeler databases also, where in a very easy way, uploading a unknown sequence, a whole protein modeling can be done stepwise. So this one is Modbase, which implies modular Python scripts only to perform 3D structure protein modeling using comparative modeling technique. So this can also be taken as a input for understanding protein structure prediction. Now we in this previous lectures we saw through Python script how we can do homology modeling, and one through open source Modbase how we can do protein modeling. Finally, the protein which we have identified and the best dope score value based structure which we have taken need to be assessed after doing MD simulation as well. So this assessment can be done through different methods. Among them, Swiss structure assessment method or structure validation is one of the prominent one, which includes Ramachandran validation and morphology assessment method. In this, SAVS, structure analysis verification server, is the most prominent method to understand the stability of a protein on the basis of Ramachandran plot, on the basis of understanding stereochemical analysis of all the amino acids present in the 2D structure of the conformation of the protein 3D structure. Among SAVs, there are different categories in which ProCheck is the most prominent one, which gives us the assessment of the protein using Ramachandran plot. So, in this whole lecture, what we have understood is to do protein modeling using homology modeling technique used by modeler. We went in modeler and we did a Python script protein modeling and we generated a model. Second, we also saw that how on the basis of graphical user interface way we can do protein modeling by Modways. Third, we also saw that protein which has been modeled need to be went through structure validation, that is assessment. So, to summarize all, modeling using homology depends heavily on the quality of the sequence alignment and the incomplete structure. Modeler is based on Python script and on the basis of satisfaction of spatial restraints for constructing the model. Minimum knowledge of the Python script is required to perform this activity. The best model is the result of many iterations and basic steps which improves the quality of each step and modeled protein is been identified. SAVs, Swiss structure assessment and process are used to help in model validation. So, these all strategies helps in quality improvement and better understanding of the modeled 3D protein structure. So, thank you and happy modeling for this protein structure.